Hello, in this lecture we will find the length of chord AB. In the drawing we have a semicircle. Inside this semicircle we have 3 circles. Those 2 small circles are identical, and the middle circle is tangent to the semicircle at point O, and the point O is also the center of the semicircle, and point C is the center of the middle circle, and we know that PQ equals to 8 units, and PQ, it is actually the diameter of the semicircle. PQ is the diameter of the semicircle, and it equals to 8 units, and the diameter of any circle or semicircle is twice as large as the radius. So if PQ equals to 8 units, that is the diameter of this semicircle, then the radius of this semicircle will be half of it. That is to say, the radius will be equal to 4 units. Therefore, PO, that is the radius of this semicircle, will be equal to 4 units. So PO equals to 4 units. And OQ, that is also the radius of the semicircle, will be equal also to 4 units. And we also know that AB is parallel to PQ. OX is also the radius of the semicircle, therefore it equals to 4 units. But OX is also the diameter of this middle circle, and as I already said, the diameter is twice as large. The diameter is twice as large as the radius. So if the diameter of this middle circle equals to 4 units, then the radius of this middle circle will be equal to 2 units. So CO will be equal to 2 units. That is the diameter of this middle circle, and CX, that is also the diameter of this middle circle, will also be equal to 2 units. And this is the center of the small circle. We will define the center of this small circle as point M. Then we will join together points M and C by a straight line. MC, it is actually the distance between the centers of those 2 circles. This is the distance between the small circle, the center of the small circle, and the distance between the center of the middle circle. And we have a rule that when 2 circles have an external length between them, like in this drawing, the small circle is tangent to the middle circle at this point. We define this point as point Y. So when 2 circles have an external length between them, then the distance between their centers is equal to the sum of the lengths of their centers, and the sum of the lengths of their radiuses. So the length of the radius of the small circle is r. According to our definition, the radius of the small circle is r, and the radius of the middle circle equals to 2 units, so the length of the radius is equal to 2 units. So in total, MC, that is the distance between the centers of those two circles, equals to r plus 2. Okay. Then we will define the touching point between tangent PQ and this small circle as point N. And we will join together points M and N by a straight line. Actually, MN is the radius of this small circle, that is to say it equals to R. And we have the rule that states that whenever the radius is drawn to the point of tendency, like in this drawing, we have the radius MN that is drawn to the point of tendency, that is to say it is drawn to point N, that is the point of tendency of tangent PQ with this small circle. Then the tangent PQ will be perpendicular to this radius, that is to say this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Okay, likewise, the radius CO of the middle circle that equals to 2 units is drawn to the point of tangency, that is to say it is drawn to point O, that is the point of tangency of tangent PQ with this middle circle. Therefore, according to the rule that I mentioned, the tangent PQ will be perpendicular to this radius, that is to say this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Okay, so in the next step we will draw perpendicular from point M to OC. So this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. And we will define the touching point between the perpendicular from point M to CO as point D. And here we know that AB is parallel to PQ. AB is parallel to PQ, and we have a rule that states that corresponding angles between parallel lines are equal to each other. So those two angles are defined as corresponding angles, and therefore they are equal to each other. And we know that this angle equals to 90 degrees, so this angle will be also equal to 90 degrees. And okay, so this angle equals to 90 degrees. It is a right angle. And likewise, those two angles are actually corresponding angles that are located between the parallel lines AB and PQ. Therefore, they are equal to each other, and we know that this angle equals to 90 degrees, so this angle will be also equal to 90 degrees. because those angles are equal to each other. And in the next step, I will draw the quadrilateral MNOD and the right triangle CMD in a new page. As you can see from the drawing, quadrilateral MNOD is 3 right angles, 1, 2 and 3. We will define this point as point E. So I draw the quadrilateral MNOD that has 3 right angles, 1, 2, 3, and the right triangle CDM, and we also have here another right triangle, it is a right triangle CEY. Okay, here we have another right triangle CEY. Okay, so if you focus on the quadrilateral MNOD, in quadrilateral MNOD, as I have already mentioned, we have 3 right angles, 1, 2, and 3. and the sum of those three right angles is equals to 90 times 3 is 270 degrees. Plus the size of this angle that we will define as angle x. So the sum of the angles in any quadrilateral equals to 360 degrees. I will write rule number 1, I'll write it down. According to rule number 1, the sum of the angles in any quadrilateral equals to 360 degrees. So I will write it down. Rule number 1 states that the sum of the angles in any quadrilateral equals to 360 degrees. So I will read rule number 1 again. Rule number 1 states that the sum of the angles in any quadrilateral equals to 180 degrees. Therefore, if we focus on quadrilateral MNOD, the sum of its angles must be equal to 360 degrees. Therefore, the sum of the three angles is 270 degrees plus the size of the fourth angle must be equal to 360 degrees according to rule number 1. Okay, so here we will subtract 270 degrees from this equality, and we will get that the size of angle x it is actually equal to 360 degrees minus 270 degrees, that is to say it equals to 90 degrees. So we found out that angle x equals to 90 degrees, it is a right angle. So here angle x is a right angle, it equals to 90 degrees. So actually quadrilateral MNTO has 4 right angles. And we have rule number 2 that states that according to rule number 2, a quadrilateral with 4 right angles must be at least a rectangle if not a square, it must be at least a rectangle. So I will read rule number 2 again. Rule number 2 states that a quadrilateral with 4 right angles must be at least a rectangle. Therefore, this quadrilateral MNOD must be at least a rectangle. And we have also rule number 3. Rule number 3 states that the opposite sides of a rectangle are equal to each other. So I'll write down rule number 3. Rule number 3 states that the opposite sides of a rectangle are equal to each other. So I will read rule number 3 again. According to rule number 3, the opposite sides of a rectangle are equal to each other. So here, as you can see from the drawing, MN is the radius of this small circle. It equals to R. So here we can write down that MN is the radius of the small circle, is equals to R. And according to rule number 3, that the opposite sides of a rectangle are equal to each other, MN equals to DO. Okay, MN equals to DO. MN equals to DO according to this rule number 3 that says that the opposite sides of a rectangle are equal to each other. Okay, but we know that MN equals to R. MN equals to R. You can write here that MN equals to R, and from this equality we will conclude that DO also equals to R. DO equals to R, so we can write here that DO equals to R. And what is the value of CO? The value of CO, it is actually the radius of the semicircle. You can see here that CO is the radius of the semicircle. That is to say, it equals to 2 units. So CO, that is the radius of the semicircle, it equals to 2 units. So we can write here that CO equals to 2 units. CO minus DO equals to CD. Again, CO minus DO equals to CD. Okay, CO minus DO equals to CD. CD equals to CO minus DO. I will repeat again, CD equals to CO minus DO. You can see it from the drawing. So CD equals to CO, that is 2 units. CO, it is 2 units, and DO equals to R. So CD equals to 2 minus R. So we can write here that CD, the size of CD, it is actually 2 minus R. The size of line segment CD is 2 minus R. And we have already found out that CM, that is the distance between the centers of the small circle and the center of the middle circle, equals to R plus 2, because R is the radius of the small circle and 2 is the radius of the middle circle. So in total, CM equals to R plus 2. So we can write here that CM it is actually equal to R plus 2. Okay? CM equals to R plus 2. And we know that CD equals to 2 minus R. So we will focus on the right triangle, triangle CDM. On the right triangle, triangle CDM, according to the Pythagoras theorem that states that the square of the hypotenuse equals to the sum of the squares of the perpendiculars, so if we relate to the right triangle, triangle CDM, we will get that the square of the hypotenuse of the right triangle, triangle CDM is CM, and the square of the hypotenuse is CM square, and according to the Pythagoras theorem, it equals to the sum of the squares of the perpendiculars. That is to say, it equals to CD square plus MD square. So I will repeat again. According to the Pythagoras theorem, in the right triangle, triangle CDM, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say CM square equals to CD square plus MD square. Okay, but we have already found out that CM equals to R plus 2. If CM equals to R plus 2, then CM square will be equal to R plus 2 square. CD, we have already found out that CD equals to 2 minus R. If CD equals to 2 minus r, then CD square will be equal to 2 minus r square. I repeat again. Cm equals to r plus 2, so Cm square will be equal to r plus 2 square. CD equals to 2 minus r, and CD square will be equal to 2 minus r square. MD square is MD square. So here we will open the brackets on both sides of equation number 1, this equation, and we will get that r plus 2 square is actually equal to r square plus 4r plus 4, and it equals to 2 minus r square. 2 minus r square equals to 4 plus r square minus 4r plus md square. So here we have r square on both sides of this equation, equation number 1, so r square will get cancelled, and we also have 4 on both sides of equation, this equation, equation number 1, so 4 will also get cancelled. And what is left from equation number 1 after we cancel those expressions? What is left? It is actually in this side of the equation we have 4r, and in this side of the equation we have minus 4r plus md square. So I write it down. So here what is left is 4r, and on the other side of equation number 1, this equation, what is left, it is actually minus 4r plus md square. So here we will add 4r to this equation, equation number 1, and we will get that 4r plus 4r is 8r. 8r equals to md square, because 4r minus 4r is 0. In total we got that 4r equals to md square. So here we will take a root out of equation number 1, and we will get that md equals to the square root of 8r. Okay, so we got that md, after we took a root out of equation number 1, we got that md equals to the square root of 8r. We know that 8 is 4 times 2, so I write it down. So we get that md equals to the square root of, we'll substitute 8 by 4 times 2. So here the square root of 4 is 2, so I will write it down. And we will get that MD, according to equation number 1, equals to the square root of 4 is 2, it equals to 2 times the square root of 2r. We found out that MD equals to 2 times the square root of 2r. So we can write here that MD equals to 2 times the square root of 2r. Okay, MD equals to 2 times the square root of 2r. And according to rule number 3, that the opposite sides of a rectangle are equal to each other, we will get that MD equals to NO. MD equals to NO, according to rule number 3, that the opposite sides of a rectangle are equal to each other. According to rule number 3, that the opposite sides of a rectangle are equal to each other, MD equals to NO. And we know, we already found out that MD equals to 2 times the square root of 2r. MD equals to 2 times the square root of 2r. So from this equality, we will get that NO also equals to 2 times the square root of 2r. NO also equals to 2 times the square root of 2r. Okay, so we can write here that NO equals to 2 times the square root of 2r. In the next step, we will join together points M and O by a straight line. So we join together points M and O by a straight line, and we will focus on the right triangle, triangle M and O. And we will also join together points M and O. We will join together points M and O in the original drawing. Okay, we will join together points M and O by a straight line. And we will also join together points A and M by a straight line. As you can see from the drawing, AM is the radius of the small circle, that is to say it equals to R. AM equals to R, it is the radius of the small circle. And what is the length of MO? MO, you can see from the drawing that MO equals to AO minus AM. I will repeat again. MO equals to AO minus AM. repeat again, MO equals to AO minus AM. Okay? So MO equals to AO. What is AO? AO is the radius of the semicircle. AO is the radius of the semicircle, that is to say it equals to 4 units. And we have already found out that AM is the radius of the small circle, that is to say it equals to R. So in total, we found out that MO equals to 4 minus R. MO equals to 4 minus R. So we can write here that the hypotenuse MO equals to 4 minus R. And we know, we have already found out that NO equals to 2 times square root of 2R, and we know that MN equals to R. So we will implement the Pythagoras theorem in the right green triangle MNO. According to the Pythagoras theorem in the right green triangle MNO, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is MO, therefore the square of the hypotenuse is MO square. And it equals to the sum of the squares of the perpendiculars, that is to say it equals to MN square plus NO square. So I will repeat again. In the right triangle MNO, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is MO, therefore the square of the hypotenuse is MO square, and it equals to the sum of the squares of the perpendiculars, that is to say it equals to MN square plus NO square. But we have already found out that MO equals to 4 minus R. If MO equals to 4 minus R, then MO square will be equal to 4 minus R square. Okay. MO equals to 4 minus R square. And we know that MN equals to R. If MN equals to R, then MN square will be equal to R square. Plus NO square. NO equals to 2 times square root of 2R. And NO square will be equal to 2 times square root of 2R square. So I'll repeat again. MO equals to 4 minus R, therefore MO square equals to 4 minus R square. MN equals to R, so MN square equals to R square. NO equals to 2 times square root of 2R, therefore NO square equals to 2 times square root of 2R square. So here we will open the brackets on both sides of equation number 2, and we will get that 4 minus R square equals to 16 plus R square minus 8R, and it equals to R square plus the square of 2 times square root of 2r is 8r. So here we have r square in both sides of equation number 2, so r square will get cancelled. And we have here minus 8r and plus 8r. So we will add 8r to this equation, equation number 2, and we will get that according to equation number 2, here we have 16. We added 8r to this equation, equation number 2. 8r minus 8r is 0. So 16 equals to 8r plus 2. 8r plus 8r is 16r. So we actually found out that according to equation number 2, 16 equals to 16r. Found out that 16 equals to 16r. We will divide this equation, equation number 2, by 16, and we will get that r equals to 16 over 16. That is to say, r equals to 1 unit. R equals to 1 unit. So we will write here that r equals to 1 unit. Here also r equals to 1 unit. And here we found out that CD equals to 2 minus r, and r equals to 1. So CD equals to 2 minus 1, that is to say it equals to 1. So CD equals to 1 unit also. CD equals to 1 unit. So in the next step, we will focus on the right triangle, triangle CEY, and we will also focus on the right triangle, triangle CDM, and we will prove that those two right triangles are similar to each other. So we will focus on the right triangle, triangle CEY, and we will focus also on the right triangle, triangle CDM, and we will prove that those two right triangles are similar to each other. I will repeat again. We will focus on the right triangle, triangle CEY, and on the right triangle, triangle CDM. First of all, we know that those two angles, they are equal to each other. They are both equal to 90 degrees. So angle CEY of triangle CEY, this angle equals to angle CDM of triangle CDM, and both angles are right angles. They are equal to 90 degrees. So angle CEY equals to angle CDM, and both angles, they are equal to 90 degrees. Okay, and we also know that this angle, angle C, is a common angle. It belongs to both triangles. It belongs to triangle CEY, and angle C also belongs to triangle CDM. So we can write down that angle C equals to angle C is a common angle that belongs to both triangles. Angle C equals to angle C. It is actually a common angle that belongs to both triangles. repeat again. Angle C equals to angle C. It is a common angle that belongs to both triangles. And those two angles, they are also equal to each other according to third angle theorem. So actually, this angle, that is angle CYE, equals to this angle, that is actually angle CMD. And they are equal to each other according to third angle theorem. I will repeat again. Angle CYE equals to angle CDM, and they are equal to each other according to third angle theorem. So, what is third angle theorem? Third angle theorem is that states that if two angles in one triangle congruent to two angles in another triangle, then the third pair of angles must also congruent. Okay, so here, actually in the previous lecture, I proved the third angle theorem. So here we proved that the first pair of angles, they are equal to each other, they are right angles. The second pair of angles, it is actually angle C that equals to itself, it is a common angle. So we have here two pairs of angles that congruent. Therefore, the third pair of angles must also congruent, that is to say angle CYE from triangle CYE equals to angle CDM, this angle from triangle CDM. Those two angles are equal to each other according to third angle theorem. So we actually proved that all three angles of triangle CEY congruent to all three angles of triangle CDM. All three angles of triangle CEY, 1, 2, 3, congruent to all three angles of triangle CDM, 1, 2, 3. Therefore, we proved that triangle CEY is similar to triangle CDM according to angle similarity rule. So I'll write it down. We actually proved the triangle CEY is similar. This is the sign of similar to triangle CDM according to angle similarity rule. So I will read it again. We actually proved that triangle CEY is similar to triangle CDM according to angle similarity rule. So what is angle similarity rule? Angle similarity rule is that if you prove that all angles in one triangle congruent to all three angles in another triangle, then you actually proved that those two triangles congruent to each other, and those two triangles similar to each other according to angle similarity rule. And from the fact that the triangle CEY is similar to triangle CDM, we will conclude that the following equality is true. we will actually conclude that CE over CY in triangle CY, CE over CY in triangle CYE equals to CD over CM, CD over CM in triangle CDM. I will repeat again. We conclude that the following equality is true, that CE over CY in triangle CY equals to CD over CM in triangle CDM. So actually CE over CY. What is the value of CY? You can see here that CY equals to 2 units. It is the radius of the middle circle. So CY equals to 2. Okay, so CE over CY is CE over 2 because CY equals to 2. And it equals to CD. We've already found out that CD equals to 2 minus R and R equals to 1, so CD equals to 1 unit. So CD is 1 over CM. CM is R plus 2. R is 1, so R plus 2 is 1 plus 2. 1 plus 2 is 3. So CM equals to 3 units. So CE over CY is CE over 2. It equals to CD over CM. CD is 1 and CM is 3. So in total we got that CE over 2 equals to 1 over 3. Here we will multiply equation number 3 by 2 and we will get that CE equals to 2/3, 2 over 3. C equals to 2/3 or 2 over 3 units. So we can write here that CE equals to 2 over 3 or 2/3. And what is the value of ED? You can see from the drawing that ED equals to CD minus CE. ED equals to CD minus CE. Again, from the drawing you can see that ED equals to CD minus CE. But we have already found out that CD equals to 1 and CD equals to 2/3. C equals to 2 over 3. So ED will be equal to 1 minus 2 over 3, that is third. ED equals to third, so we can write here that ED equals to third. And what is the value of OE? The value of OE, you can see from the drawing that OE equals to OD plus ED. So OE, you can see from the drawing that OE equals to OD plus ED. OD plus ED. So OE equals to OD, that is R, that equals to 1, plus ED, that is third. So in total we got that OE equals to 1 plus third. 1 plus third is 4 over 3. 1 plus third is 4 over 3. So OE equals to 4 over 3 units. OE equals to 4 over 3 units. So we can write here that OE equals to 4 over 3 units. OE equals to 4 over 3 units. In the next step, we will join together points O and B by a straight line. And we will find out the size of this angle. Actually, OEX is the diameter of the middle circle. OX is the diameter of the middle circle, and therefore it is a straight line. And we know that the sum of the angles on one side of a straight line equals to 180 degrees. And we have already found out that this angle equals to 90 degrees. And the sum of the angles at one side of point E in the straight line OX must be equal to 180 degrees. So if this angle is 90 degrees, this angle must be also equal to 90 degrees, because it must complete the sum of the angles on one side of point E to 180 degrees. So if this angle is 90 degrees, this angle must be also equal to 90 degrees in order to complete the sum of the angles on this side of point E to 180 degrees. So this angle is a right angle. And if this angle is a right angle, then triangle OEB is a right triangle. So angle OEB, this angle is a right angle. Okay, so angle OEB is a right angle, it equals to 90 degrees, therefore triangle OEB is a right triangle, and OB is the radius of the semicircle, that is to say it equals to 4 units. And we have already found out that OE equals to 4 over 3 units. So I will copy again the right triangle OEB. Angle OEB is a right angle, it equals to 90 degrees. So I copied the right triangle OEB. We have already found out that OE equals to 4 over 3 units, and OB is the diameter of the semicircle, therefore it equals to 4 units. The only thing that is left to find is to find out the size of side EB, and we will find it according to the Pythagoras theorem, that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle OEB, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the hypotenuse is OB, so the square of the hypotenuse is OB squared, and it equals to the sum of the squares of the perpendiculars. That is to say, it equals to OE squared plus EB squared. I'll repeat again. In the right triangle OEB, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, OB squared equals to OE squared plus EB squared. But we know that OB equals to 4 units, so OB squared is 4 squared. 4 squared is 16. It equals to OE squared. OE is 4 over 3, so OE squared is 4 over 3 squared plus EB squared. So I'll repeat again. OB equals to 4, so OB squared is 4 squared. 4 squared is 16. Equals to OE squared. OE is 4 over 3, so OE squared equals to 4 over 3 squared plus EB squared. 4 over 3 squared is 16 over 9, so I'll write it down. Sixteen equals to 16 over 9 plus EB squared. So here we will subtract 16 over 9 from this equation number 4, and we will get that 16 minus 16 over 9 equals to EB squared. Here we will multiply 16 by 9, and then we will divide it by 9 in order to have a common factor with 16 over 9. So we will get that 16 times 9 over 9 minus 16 equals to EB squared. Here 16 times 9 minus 16 is 16 times 8. So in total we will get that 16 times 8 over 9 equals to EB squared. Here we know that 16 is 2 times 8, so I'll write it down. We will substitute 16 by 2 times 8. So 2 times 8 times 8 over 9 equals to EB squared. So we substituted 16 by 2 times 8 and we got this expression. Here we take a root out of this equation, equation number 4. And we will get that the square root of 2 times 8 times 8 over 9 equals to EB. So here the square root of 8 times 8 is 8 and the square root of 9 is 3. So in total we will get that, according to equation number 4, 8 over 3 times square root of 2 equals to EB. So we found out the value of EB. EB equals to 8 over 3 times square root of 2 units. Okay, EB equals to 8 over 3 times square root of 2 units. In the next step, we will prove that those two right triangles can go into each other. So we will prove that the right triangle OEB, right great triangle, triangle OEB is congruent to the right great triangle, triangle OEA. Okay, so I will copy again those green right triangles and we will prove that they can go into each other. Okay, so I copied again those two right triangles. We know that AO equals to OB. It is they are the radiuses of the semicircle, so OA equals to OB equals to 4 units. They are the radiuses of the semicircle, and we also have side OE is a common side, it belongs to both triangles, so OE equals to OE is a common side that belongs to both triangles. So in this way, by these two identities, we actually managed to prove the triangle OEA is congruent. This is the sign of congruent to triangle OEB, and they are congruent to each other according to rule number 4. So I will write down rule number 4. According to rule number 4, or rule number 4 states that if the hypotenuse and the perpendicular of one right triangle congruent to the hypotenuse and a perpendicular in another right triangle, then the right triangles congruent to each other. Congruent to each other. So I will read rule number 4 again. Rule number 4 states that if the hypotenuse and the perpendicular of one right triangle congruent to the hypotenuse and the perpendicular to another right triangle, then the right triangles congruent to each other. And we actually proved that the hypotenuse OB and the perpendicular OE in triangle OEB congruent to the hypotenuse OA and the perpendicular OE in the right triangle OEA. Therefore, we proved that according to rule number 4, those two right triangles congruent to each other. And from the fact that those two right triangles congruent to each other, we will conclude that AE equals to EB, AE equals to EB, according to the rule that corresponding sides in congruent triangles are equal to each other. We conclude that AE equals to EB according to the rule that corresponding sides in congruent triangles are equal to each other. Those two right triangles congruent to each other. Therefore, the two corresponding sides AE and EB, they are equal to each other. That is to say, AE equals to EB. And what is the value of AB? From the drawing, you can see that AB equals to AE plus EB. AE plus EB. From the drawing, you can see that AB equals to AE plus EB. But we have already found out that AE equals to EB. So we can substitute AE in this equality by EB because AE equals to EB. So we will get that AB equals to EB plus EB. That is to say AB equals to 2 times EB. And we have already found out that EB equals to 8 over 3 times square root of 2 units. So in total we got that AB equals to 2 times 8 is 16 over 3 times square root of 2 units. We found out that AB equals to 16 over 3 times square root of 2 units, or in terms of numbers, AB equals to 7.54 units. So I'll repeat again. The length of chord AB equals to either 16 over 3 times square root of 2 units, or in terms of numbers, the length of chord AB equals to 7.54 units. I will repeat again. We'll see it on the drawing itself. Here, this chord AB, the length of chord AB equals to either 16 over 3 times square root of 2 units, or in terms of numbers, the length of chord AB equals to 7.54 units. Okay, so now I'll summarize the lecture. Actually, we wanted to find out the length of this chord AB, and we know that we have a semicircle, and inside the semicircle we have 3 circles. So inside this semicircle we have 3 circles. Those 2 small circles are identical, and we have the middle circle. The middle circle is tangent to the semicircle at point O. Point O is also the center of the semicircle, and point C is the center of the middle circle. We know that PQ equals to 8 units, and the radius is half of the diameter. The diameter PQ equals to 8 units, therefore the radius of the semicircle will be equal to half of it, that is to say it will be equal to 4 units, that is to say PO, the radius of the semicircle, equals to 4 units, and OQ, that is also the radius of the semicircle, will be equal to 4 units. But OX, it is not only the radius of the semicircle, but it is also the diameter of the middle circle, and the diameter is twice as large as the radius. So if the diameter of the middle circle equals to 4 units, then the radius of the middle circle will be equal half of it, that is to say it will be equal to 2 units. So OC, the radius of the middle circle, will be equal to 2 units, and CX, the radius of the middle circle, will be also equal to 2 units. And we also know that AB is parallel to PQ. Okay? And we join together points M and C by a straight line. M and C are the centers of the small circle and the middle circle. And the distance between the centers of 2 circles that have an external notch between them, it equals to the length of their radiuses, that is to say MC equals to R, that is the radius of the small circle, plus 2, that is the radius of the middle circle. So MC equals to R plus 2. Then we join together points M and N by a straight line. MN is the radius of this small circle. So the radius MN is drawn to the point of tangency, that is to say it is drawn to point N, that is the point of tangency of tangent PQ with this small circle. Therefore, according to the rule that whenever you have a radius that is drawn to the point of tangency, then the tangent PQ will be perpendicular to this radius. That is to say, this angle equals to 90 degrees and this angle also equals to 90 degrees. Likewise, the radius TO is drawn to the point of tangency. That is to say, it is drawn to point O, that is the point of tangency of tangent PQ with this middle circle. Therefore, according to the rule that I mentioned, the tangent PQ will be perpendicular to this radius CO. That is to say, this angle equals to 90 degrees and this angle also equals to 90 degrees. Then, from point M, that is the center of the small circle, we draw perpendicular to CO. So this angle is 90 degrees and this angle is 90 degrees, and we define the touching point between the perpendicular from point M to CO as point D. Then we know that AB is parallel to PQ, and here we have a rule that states that corresponding angles between parallel lines are equal to each other. Therefore, those two angles that are located between the parallel lines AB and PQ, those two corresponding angles will be equal to each other. So if this angle is 90 degrees, then this angle will be also equal to 90 degrees. Likewise, on the other side, we know that this angle equals to 90 degrees, so this angle must be also equal to 90 degrees because of the fact that those two corresponding angles that are located between the parallel lines AB and PQ must be equal to each other. So those two angles are right angles and those two angles are also right angles. Then we know that in quadrilateral MNOD, we have three right angles, 1, 2, 3. And we have the rule that states that the sum of the angles in any quadrilateral equals to 360 degrees. Therefore, the sum of the angles in quadrilateral MNPO must be equal to 360 degrees, and quadrilateral MNPO has already three right angles, 1, 2, 3. So the sum of those three right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is defined as angle X, must be equal to 360 degrees according to rule number 1. That is to say, 270 degrees plus the size of angle X must be equal to 360 degrees. Here we subtracted 270 degrees from this equality, and we got that the size of angle X is actually equal to 90 degrees. It is a right angle. Therefore, actually this is a right angle, all three angles in quadrilateral MNOD are right angles. And we have the rule that states that any quadrilateral that has four right angles, it is at least a rectangle. A quadrilateral, rule number 2 states that a quadrilateral with four right angles must be at least a rectangle. So this quadrilateral MNDO must be at least a rectangle. Okay, and then we have also rule number 3. Rule number 3 states that the opposite sides of a rectangle are equal to each other. We know that MN is the radius of the small circle, that is to say it equals to R. And according to rule number 3, that the opposite sides of a rectangle are equal to each other, it means that MN equals to DO. MN equals to DO. According to rule number 3, MN equals to DO, and we already know that MN equals to R. From this equality, we will conclude that DO also equals to R. DO also equals to R. And what is the value of CD? CD, from the domain you can see that CD equals to CO, it equals to CO minus OD. Okay, CD equals to CO minus OD, but we know that CO is the radius of the middle circle, it equals to 2 units. CO equals to 2 units and DO is the radius of the small circle. That is to say it equals to R. So in total we found out that CD equals to 2 minus R. CD equals to 2 minus R. And then we focus on the right triangle CDM, and the right triangle CDM. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. And what is CM? CM equals to R plus 2. As I already showed you, CM is the distance between the centers of the small circle and the middle circle, and it equals to R plus 2. We have already found out that CD equals to 2 minus R, and we implemented the Pythagoras theorem in the right triangle CDM. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, CM square equals to CD square plus MD square. We have already found out that CM equals to R plus 2, so CM square will be equal to R plus 2 square. CD equals to 2 minus R, therefore CD square will be equal to 2 minus R square. And MD square is MD square. We open the brackets of equation number 1. R plus 2 square is R square plus 4R plus 4, and 2 minus R is 4 minus R square minus 4R. We have R square on both sides of equation number 1, so R square will get cancelled, and we have 4 on both sides of equation number 1, so 4 will also get cancelled. And what is left from equation number 1 after we cancelled those expressions? What is left? It is actually 4R equals to minus 4R plus MD square. We added 4R to this equation number 1, and we got that 4R plus 4R is 8R. And 4R minus 4R is 0, so in total we got that 4R equals to MD square. Here we took a root out of equation number 1, and we got that MD equals to the square root of 8R. MD equals to the square root of 8R. But 8 is 4 times 2. So we substituted 8 by 4 times 2, and we got that MD equals to the square root of 4 times 2R. The square root of 4 is 2, so in total we got that MD equals to 2 times square root of 2R. So here we can write that MD equals to 2 times square root of 2R. According to rule number 3, the opposite sides of a rectangle are equal to each other, so MD equals to NO. MD equals to NO according to rule number 3. But we know that MD equals to 2 times square root of 2R, so for this equality we will get that NO also equals to 2 times square root of 2R, so we can write here that NO equals to the square root of equals to 2 times the square root of 2R. Then we join together points M and O by straight line. And what is the value of MO? What is the length of MO? From the original drawing we can see we join together points O and M by straight line, and we join together points A and M by straight line. Actually, MO equals to AO minus AM. Okay, I repeat. MO equals to AO minus AM. So MO equals to AO, that is the radius of the semicircle, minus AM, that is the radius of the small circle, that is to say it equals to R. So MO equals to AO, that is 4, minus MA, that is R. In total, we found out that MO equals to 4 minus R. So here we have, know that MO equals to 4 minus R, and O equals to 2 times square root of 2R, and MN equals to R. So we implemented the Pythagoras theorem on the right green triangle. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, MO square equals to MN square plus NO square. We have already found out that MO equals to 4 minus R, therefore MO square equals to 4 minus R square. MN equals to R, so MN square equals to R square. And NO equals to 2 times square root of 2R, therefore NO square equals to 2 times square root of 2R square. Here we open the brackets of this equation number 2, and we got that 4 minus R square equals to 16 plus R square minus 8R. And here we have R square, and the square of 2 times square root of 2R is 8R. Here we have R square in both sides of equation number 2, so R square will get cancelled. Then we added 8R to equation number 2, so here 16 minus 8R plus 8R is 0, and 8R plus 8R is 16. So in total we got that 16 equals to 16R. Then we divided the equation number 2 by 16, and we got that R equals to 16 over 16, R equals to 1. So R equals to 1 unit. So here we found out that R equals to 1 unit. Therefore here R equals to 1, R equals to 1, and CD equals to 2 minus R, and R is 1, so 2 minus 1 is 1. And Cm equals to R plus 2, and R is 1, so 1 plus 2 is 3. So Cm equals to 4 units, Cm equals to 3 units, CD equals to 1 unit, and R equals to 1 unit. And then we proved that those two right triangles, triangle CEY is similar to triangle CDM. We focus on triangle CEY and triangle CDM, the right triangles, and we prove that those two triangles are similar to each other. Why they are similar to each other? Because of the fact that they have those two right triangles that are equal to each other. Angle CEY equals to angle CDM equals to 90 degrees. And we also have this angle, angle C is a common angle, it belongs to both triangles, so we can write down that angle C equals to angle C is a common angle that belongs to both triangles. And we have those two angles that are also equal to each other according to third angle theorem. What is third angle theorem? Third angle theorem says that if two angles in one triangle congruent to two angles in another triangle, then the third pair of angles must also congruent. So here we proved that those angles are equal to each other, and this angle is a common angle, it belongs to both triangles, so it equals to itself. So we proved that two pairs of angles are equal, congruent in those two right triangles. So the third pair of angles, those are the third pair of angles that also must congruent according to third angle theorem. So we actually proved that all three angles 1, 2, 3 on triangle CYE congruent to all three angles on triangle CDM. Therefore, we proved that triangle CYE is similar to triangle CDM according to angle similarity rule. So what is angle similarity rule? Angle similarity rule is that if you prove that all three angles in one triangle congruent to all three angles in another triangle, then you actually proved that those two triangles are similar to each other according to angle similarity rule. And from the fact that triangle CY is similar to triangle CDM, we will conclude that CE over CY in triangle CYE equals to CD over CM in triangle CDM. CE over CY, CY is 2, it is the radius of the middle circle. CD equals to 1 unit, CM equals to 3 units. So in total we got that CE over 2 equals to 1 over 3. We multiply the equation number 2 by we multiply the equation number 3 by 2, and we got that CE equals to 2/3. So here CE equals to 2/3 and CD equals to 1 unit. Therefore CED will be equal to CD minus CE. ED equals to CD minus CE. CD is 1 unit and CE is 2/3. So in total ED equals to 1 minus 2/3, that is to say it equals to 1/3. So DE equals to 1/3, CE equals to 2/3, CD equals to 1 unit, and R equals to 1 unit. And what is the value of OE? The value of line segment OE, it is actually OD plus ED. Okay? OE equals to OD plus ED. OD is 1, it is the radius of the small circle, and we have already found out that ED equals to 1/3. So in total OE, that is OD plus DE, it equals to 1 plus 1/3. 1 plus 1/3 is 4 over 3. So OE equals to 4 over 3. Then we actually proved, we connected together points O and B by a straight line, and then we proved that this angle OEB is a right angle. Why it is a right angle? Because we know that on this side of the straight line OX, at point E, we have here 90 degrees. Okay? Angle BEX equals to 90 degrees. And we know that the sum of the angles on one side of a straight line equals to 180 degrees. So if this angle is 90 degrees, this angle OEB must be also equal to 90 degrees in order to complete the sum of the angles at one side of point E to 180 degrees. So this angle OED equals to 90 degrees. Angle OEB equals to 90 degrees. So, okay, angle OEB equals to 90 degrees. Therefore, triangle OEB is a right triangle. So I copied again the right triangle, triangle OEB. We have already found out that OE equals to 4 over 3 units. And OB is the radius of the semicircle, that is to say it equals to 4 units, and the only thing that is left to find is to find out the length of EB. We'll find out the value of EB according to the Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse in the right triangle OEB equals to the sum of the squares of the perpendiculars, that is to say OB square equals to OE square plus EB square. OB is 4, so OB square is 4 square. 4 square is 16. OE is 3 over 4 units, so OB square will be equal to 3 over 4 square plus EB square. So 16 equals to 3 over 4 square is 16 over 9 plus EB square. We subtracted 16 over 9 from equation number 4, this equation, and we got that 16 minus 16 over 9 equals to EB square. Here we multiplied 16 by 9 and then we divided by 9 in order to have a common factor with 16 over 9, and we got that 16 times 9 minus 16 over 9 equals to EB square. 16 times 9 minus 16 is 16 times 8. So in total we got that 16 times 8 over 9 equals to EB square. Here we took a root out of equation number 4, this equation, and we got that, or before that we substituted 16 by 2 times 8 because 16 equals to 2 times 8, and we got that 2 times 8 over 9 equals to EB squared. Then we took a root out of this equation, equation number 4, and we got that EB equals to the square root of 2 times 8 over 9. The square root of 8 times 8 is 8, and the square root of 9 is 3. So in total we got that EB equals to 8 over 3 times square root of 2 units. Okay, and then we actually proved that those two green right triangles can go into each other. I copied again the two right triangles here in the new page, and we proved that those two right triangles can go into each other. Right, they can go into each other. First of all, their hypotenuse are equal to each other. OA equals to OB equals to 4 units. They are the radiuses of the semicircle, and they have a common side. OE is a common side, it belongs to both right triangles, so OE equals to itself. OE equals to OE is a common side. So by proving those two, that the hypotenuse and the one perpendicular are identical in both triangles, we proved that they can go into each other according to rule number 4. What is rule number 4? Rule number 4 states that if the hypotenuse and the perpendicular of one right triangle can go into the hypotenuse and the perpendicular of another right triangle, then the two right triangles can go into each other. And we proved that the hypotenuse and the perpendicular OE in triangle OAE can go into the hypotenuse OB in the perpendicular OE in the right triangle, triangle EOB. Therefore, according to rule number 4, we proved that those two triangles, those two right triangles can go into each other. And from the fact that those two right triangles can go into each other, we will conclude that AE equals to EB. AE equals to EB according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other. Therefore, the corresponding sides AE and EB will be also equal to each other. That is to say, AE equals to EB. And what is AB? What is the value of AB? From the domain, you can see that AB equals to AE plus EB. AB equals to AE plus EB. But we know that AE equals to EB, so we can substitute AE by EB. So AB equals to EB plus EB, that is to say AB equals to 2 times EB, and we've already found out that EB equals to 8 over 3 times square root of 2 units. So 2 times 8 over 3 times square root of 2 is actually 2 times 8 is 16, so in total we got that the length of chord AB equals to either 16 over 3 times square root of 2 units, or in terms of numbers, the length of chord AB equals to 7.54 units. I will repeat again. The length of chord AB, this chord AB, equals to either 16 over 3 times square root of 2 units, or in terms of numbers, the length of this chord called AB equals to 7.54 units. Okay, thank you very much.